when you look at that. So, pull up the periodic table. More fun to try and draw one. Okay. Okay. Thank you. Yeah, I've done this before. All right. So if you look at the periodic table, where an element is can tell you an awful lot of stuff. First of all, elements are arranged in the periodic table by increasing the atomic number, right? You start off with element number 1 up here. Start off with element number 1 up here, which is hydrogen, okay, and then helium, and then lithium, beryllium, so on and so forth, until you get up to element number 118, which has a name right now. I just don't remember what it is off the top of my head. The periodic table itself is split into 4 regions or 4 different blocks. Okay. First 2 columns over here, what do we call them? The S block is coming back. Okay. This canyon here in the middle, what's that called? B block. B block, the transition metals. Okay. Chunk over here. A block. B block, right? And then of course we've got the F block down here at the bottom. Okay. Everybody else we just got done. Now those come from the different kinds of electrons in the different shapes of sublevels that they come in, okay? The S's, of course, S stands for sphere. P, they're parabolas. D, they're double parabolas. F, I think we said they look like flowers. That works for me. And the width of each of these blocks tells you how many electrons fit. So the S's, since this thing is too wide, the S block, or an S orbital at any energy level can hold 2 electrons. D block can hold 10, P block can hold 6, F block can hold 14. Okay. Now it's also organized out the columns, the up and down columns on the periodic table. These are known as groups or families. And elements that are in a certain group all have similar properties because they all have the same number of valence electrons. Okay? You're talking about group 1, group 2, that's the alkaline metals, the alkaline earth metals. They're with very reactive metals. Everybody in this first column has got 1 valence electron that it gives away, or tends to give away in chemical reactions. All the ones in group 2 have got 2 electrons they give away. Everybody here in the D block, they tend to have either 1 or 2 valence electrons. Way over here in group 13, these guys have 3. Okay, 2 in a pair and 1 single. Everybody in groups 1, 2, 3 through 12, which is this middle part, and 13, or in other words, all of this, they give away electrons when they form chemical bonds. If they are in chemical bonds with nonmetals, then the nonmetals, which are much stronger, much more electronegative, steal the electrons. If they're bonding with other metals, then they share their electrons. Their electrons flow freely from atom to atom, which is what makes metals behave the way metals behave. It makes them great conductors, it makes them very shiny. It lets their atoms slide past each other, which makes metals very malleable. They're very easy to bend, very easy to hammer into thin sheets, stronger wires. All the stuff you learn back in junior high about metals has to do with those 1, 2, or 3 valence electrons that they hold on to very loosely. You get out beyond that into groups 14 through 18, you start to see a little bit of a change. You actually see kind of a jagged stair-stepping line thing that sort of splits the P block into the metals nonmetals, and then you've got some elements right along the stairs that tend to have properties of both. Now your nonmetals, all of these that are up here in the top right corner, and also hydrogen, what they're known for is they're known for being very, very electronegative. They are very, very attractive. They have very strong pulls on their own electrons and on electrons for other atoms. So when they form chemical bonds, they are going to tend to either share electrons with other nonmetals in a covalent bond, or they're going to steal electrons from metals in an ionic bond. And so they tend, whenever they become ions, they take electrons, they tend to take on negative charges. Whereas the metals, all of these cats way over on this side, they all tend to take on positive charges. Okay? Metals become cations, nonmetals become anions. The rows on periodic table, kind of coming back to that, rows going left and right, these are what are called periods. Okay? And so you've got period 1, period 2, period 3, all the way down through, I believe, period 7. And that just tells you how many main energy levels that atom has. The ones up in period 1 are just hydrogen and helium. There's only space in that first energy level for 2 electrons. With 2 electrons, that level is full. Every other row after that will take on an increasingly large number of electrons. Okay? Period 2 has space for 8. Okay? You've got 2 here in the S. You've got 6 here in the P. Once they've got that full set of 8 in their valence shell and their outermost level of electrons, they're stable. The elements here in group 18 are superstable. They're the noble gases. Okay? They don't react with other atoms because they don't need to. They've got all the electrons they need. Okay? They've got that full set of 8. Starting with period 3, you start to see some overlap in between those different energy levels. And so you end up going in order of your 1s and your 2s, your 2p, 3s and 3p, 4s, and then you get to this first row in the D block, which is actually 3d. Okay, it comes after 4s. It's something called delayed filtering. And what that basically means is that your valence electrons are always just going to be s and p electrons. Okay, you're always just going to have s and p electrons that are in your outermost energy level. They're the ones that are involved in all the chemical bonds. What else? Okay. Properties, groups, and families, reactivity, electronegativity, types of bonds. Okay. Flashback of that. So any questions before I switch slides? Okay. So let's talk about the 3 kinds of bonds. Okay, we've got ionic, we've got covalent, and we've got metallic. Okay. Ionic bonds happen when you've got a metal and you've got a nonmetal. Okay. The metal, like I said, has either 1 or 2 or 3 valence electrons. Those electrons end up getting transferred to the nonmetal, which makes the nonmetal a negative ion, and it makes the metal a positive ion. When they have different charges like that, that difference in charge causes them to attract each other in all directions. And typically in an ionic compound, you're not going to have just like 1 or 2 atoms. You're going to have a whole lot, okay? Because those going to do is they're going to actually end up making lots and lots of in all directions, and what you're going to end up getting with an ion compound, you're going to end up getting a crystal. Okay, sometimes also called a salt. It's just an ion compound that's got a whole lot of positive and a whole lot of negative ions that are attracting each other. The ratio of sizes of those different atoms actually determines what the shape of the crystal is. With something like sodium chloride, they end up making little cubes. And so any salt crystal that is made of sodium and chloride ions, it's a cube. You take it, you smack it with a hammer, breaks into a whole lot of other little pieces, they're all cubes. Okay? And that's defined at the atomic level. Covalent compounds are going to be between nonmetals and nonmetals. And since they're all very strong, they're all very highly electronegative, what they're going to do is they're going to share electrons in either single or double or triple bonds. And it's going to be, any of those shared pairs are going to be just between the two atoms where those electrons are involved. It's not going to be an omnidirectional thing like we have with the ion. Okay. Covalent bonds, because they're sharing electrons, they tend to be a lot stronger than ion bonds. But you also can't get just these huge crystals, okay? They're typically much smaller. Now there are exceptions. You start getting into biomolecules like your DNA and your RNA and proteins. Those are big, okay? But those are the exceptions. Those aren't the rule. Most covalent substances are very, very small molecules. And whereas with metallic, you've just got metals. Again, you're going to have a whole lot of these metals, and the electrons are going to end up bouncing from atom to atom, okay, and flowing freely, okay, where they're just being shared. And again, that's what makes metals metals. They are very, very loose with their electrons. They don't hold on to them real tightly. They have no problem sharing them with their neighbors. Going back to our periodic table. Wow, what a mess. So depending on how many valence electrons an atom has, that will determine its chemical properties, how it reacts, how many electrons it needs to become stable, or how many electrons it is trying to get rid of. Generally speaking, the most reactive elements on the periodic table, quickie here. Okay. Your most reactive elements, your most reactive metals are going to be these in group 1. And your most reactive nonmetals are going to be these right here in group 17. Okay. The ones in group 1 are the alkali metals. They are very reactive because they just need to get rid of one electron, and it's very easy to do so. The ones in group 17 have 7 valence electrons. They just need one. And so it's very easy for them to obtain one more and become stable. You become less reactive as you move in. And of course, the complete least reactive is group 18. Super interactive. And of course, things like the names of the different families, you're going to have your periodic table when you take these quizzes, and you can just look them up. Okay? So, don't forget to plan that. But I've got all the words to do. I think that's the both of property groups and families and how that determines reactivity, or connectivity types of bonds. One more thing, what's the most electronegative element there is, aka the most attractive one? Fluorine, exactly. Okay. Check right here. Okay. F for fluorine.